Hello student, good morning. Today I am going to discuss dual behavior of electromagnetic radiation. The particle nature of light posed a dilemma for scientists. On the one hand, it could explain the black body radiation and photoelectric effect satisfactorily, but on the other hand, it was not consistent with the known wave. But on the other hand, it was not consistent with the known wave behavior of light, which could account for the phenomena of interference and diffraction. Actually, diffraction is bending of waves, and interference means combination of same waves having same wavelength or different wavelength. The only way to resolve the dilemma was to accept the idea that light possesses both particle and wave-like properties. That is, light has dual behavior. Depending on the experiment, scientists find that light behaves either as a wave or as a stream of particles. Whenever radiation interacts with matter, it displays particle-like properties. In contrast to the wave-like properties like interference and diffraction, which it exhibits when it propagates. This concept was totally alien to the way the scientists thought about matter and radiation, and it took them a long time to become convinced of its validity. It turns out that some macroscopic particles, macro, MIC, small, MIC, macroscopic particles like electrons, protons, macroscopic particles like electrons, particularly electrons, also exhibit this wave particles duality. This I have discussed about the dual behavior of electromagnetic radiation. Means here dual behavior means that wave behaves like both, like wave as well as particle, and so many properties has been explained only on the basis of this concept. Sometimes wave behaves like electromagnetic wave. What we are telling, it functions in both way, particularly electrons. Microscopic, here electron we can take example, it behaves like both as wave as well as particles. Then in the beginning, scientists were thinking that it behaves only like a wave, that it was unable to explain so many properties. But when they considered both as a particle, as a wave, then they were able to explain the so many properties. Now I am going to discuss evidence for the quantized electronic energy levels, that is atomic spectra. This is very, very important. That is, what are the evidence for quantized electronic energy level? Quantized electronic energy level means that in atom so many orbits are there, maybe so many orbits. Then between the two orbits some gap will be there, energy gap will be there, and these electrons, after getting energy, they will not flow like water. They will directly jump. After getting suitable energy, it will jump from one energy level to other energy level. Not it will flow like water. Then this energy gap between the two orbits, actually orbit is also called cell, SHELL, cell. Energy level, cell, orbit, three names are there, but recent name is energy level. Then between the two energy level or two orbits or two cell, some energy gap is there. They have fixed energy. That fixed energy is called quantized. Then here I am going to discuss here evidence, proof. Proof for the quantized electronic energy level. That is also called atomic spectra. By atomic spectra, you will come to know, that is evidence you will come to know by the atomic spectra. Now I am discussing. The speed of light depends upon the nature of the medium through which it passes. As a result, the beam of light is deviated or refracted from its original path as it passes from one medium to another. It is observed that when a ray of white light is passed through a prism, the wave with shorter wavelength bends more than the one with a longer wavelength. Since ordinary white light consists of waves with all the wavelengths in the visual range, a ray of white light is spread out into a series of color bands called a spectrum. Already you know that light consists of 7 colors. The light of red color, which has longest wavelength, is deviated the least. That's why a rising sun and setting sun looks or appears red, because their wavelengths are longest. It does not deviate, but sky appears blue because blue light its wavelength is very short, means frequency is high, then it spreads very fast. That's why sky looks appear, and this setting sun and rising sun looks red because red has longest wavelength, and morning and evening means rising and setting sun. Sun will be farthest from us, maximum distance both time. Then other light except you can say wave, except red, other radiation except red you can't see. We see only that radiation whose wavelength is highest. That's why red has maximum wavelength. You see only red. while rising and setting sun. That's why sun appears red and sky appears blue, because that blue light spreads fast. Its frequency is high or wavelength is less. Okay. Then due to the longest wavelength, light deviates the least, while the violet light, which has the shortest wavelength, is deviated the most. The spectrum of white light that we are knowing range from violet at 7.5 into 10 to the power 14 Hz to red at 4 into 10 to the power 14 Hz. Such a spectrum is called continuous spectrum. Again, I am telling you, the spectrum of white light that we know range from violet at 7.5 into 10 to the power 14 Hz to red at 4 into 10 to the power 14 Hz. Such a spectrum is called continuous spectrum. Continuous because violet merges into blue, blue into green, and so on. A similar spectrum is produced when a rainbow you know, it is formed in the rainy season. A similar spectrum is produced when a rainbow forms in the sky. Remember that visible light is just a small portion of the electromagnetic radiation. When electromagnetic radiation interacts with matter like atoms and molecules, may absorb energy and reach to a higher energy state. With higher energy, these are in an unstable state or excited state. For returning to their normal means more stable. Normal state means more stable. For returning to their normal state from higher in a excited state, lower energy states. Actually, this normal state is also called lower energy state, and excited energy state is called higher energy state. Then, for returning to their from higher state to the normal state, I am talking about. For returning to their normal states or energy state, normal or lower energy state, the atoms and molecules emit radiation in various regions of the electromagnetic spectrum. Means in a very simple way, from when electron returns from higher energy level to the lower energy level, they emit a different type of radiation. Okay. Now I am going to discuss emission and absorption spectra. This is very, very important from examination point of view. In so many examination, this is asked. In almost in all examination, this is asked. Emission and absorption spectra. The spectrum of radiation emitted by a substance that has absorbed energy is called an emission spectrum. Again you listen. The spectrum of a radiation emitted by a substance that has absorbed energy is called an emission spectrum. Atom, molecules or ions that have absorbed radiation are said to be excited. To produce an emission spectrum, energy is supplied to a sample of molecules or atoms. To produce an emission spectrum, energy is supplied to a sample by heating it or irradiating it, and the wavelength also you can tell frequency, irradiating it, and the wavelength of the radiation emitted as the sample gives up the absorbed energy is recorded. An absorption spectrum is like the photographic negative of an emission spectrum. A continuum of radiation is passed through a sample which absorb radiation of certain wavelength. The missing wavelength, which correspond to the radiation absorbed by the matter, leave dark space in the bright continuous spectrum. Here you should understand, I told you the missing wavelength which correspond to the radiation absorbed by the matter leave dark space in the bright continuous spectrum. Actually, this when light or radiation is absorbed by the atom or molecules, then when they are absorbing, that times they will be at normal state, means lower energy level. That's why it absorbs. It will not emit that time. Only it will absorb. After that, slowly and slowly, they will absorb more and more, and when that will become excited state, that time, again from the excited state, they want to come down again to the lower state. Then that's why from excited state they want to come to the lower state. Then that time, whatever energy they absorbed, they want to release in then different type of a spectrum, means they will release different type of radiation. Hence you will get different type of you can say light, different type of light you will get, or radiation you will get. Then that's why that is called as emission spectrum, because from excited state, while from excited state they want to come to the lower state, then they release so many, you can say, radiation of different color. But in the beginning, when they absorbed, when they were in a lower state, normal state, that time they absorbed. Hence, that time no emission. That's why it will be dark. That's why it will be dark, and that is called absorption spectrum. The study of emission or absorption spectra is referred to as spectroscopy. Actually, this is studied, all these things, emission spectra or absorption spectra is studied in spectroscopy. The spectrum of the visible light, as we have discussed, was continuous as all wavelength red to violet of the visible light are represented in the spectra. The emission spectra of atoms in the gas phase, on the other hand, do not show continuous spread of wavelength from red to violet. Rather, they emit light only at a specific wavelength with dark space between them. Such spectra are called line spectra or atomic spectra, because the emitted radiation is identified by the appearance of bright lines in the spectra. Now I am going to discuss line emission spectra. What is the line emission spectra? Actually, what I discuss now, that this while coming from excited state to the normal state, they emit so many radiation of different color, but it is not continuous. Sometimes in the middle, darkness you will get, darkness. That's why it is not continuous. Then this is a dark spectra. This is called dark space. That is called absorption spectra. Dark space is called absorption spectra with dark space, because this some light is absorbed. That's why they will get dark. It is not continuous. Now I am going to discuss line emission spectra. Line emission spectra are of great interest in the study of electronic structure of atom. Each element has a unique line emission spectrum. Each element has a unique line emission spectrum. The characteristics line in atomic spectra can be used in chemical analysis. The characteristics lines in atomic spectra can be used in chemical analysis to identify unknown atoms in the same way as fingerprints are used to identify people. The exact matching of lines of the emission spectrum of the atoms of a known element with the lines from an unknown sample quickly establishes the identity of the latter. German chemist Robert Bunsen was one of the first investigators to use the line spectra to identify elements. Elements like rubidium, cesium, thallium, indium, gallium, and scandium were discovered when their minerals were analyzed by a spectrographic method. The element helium was discovered in the sun by a spectroscopic method. Actually, this is very important. Line emission spectra is very important. Just it is used in identifying unknown element. How? Just like a fingerprint, just like every person has different fingerprint, hence every element has a different line spectra. Every element which we don't know element, that element again will have different line spectra. Known is different, unknown is different. Then whenever they got different line spectra, they concluded that this is the new element. It should not match. Matching means same element. Not matching means different element. Then by matching this line spectra, scientists concluded, particularly Bunsen, I told you, they found out so many, you can say, they identified so many elements like cesium, thallium, indium, gallium, scandium, they just differentiated. Hence, line emission spectra is very, very important. Now, I will discuss some numericals based on, I can say, dual behavior of electromagnetic radiation, because numericals is also asked in different type of competitive examination. Then now, last class also I discussed so many numericals. Here also I want to discuss some numericals, and actually here in real sense I want to discuss concept. Concept is very, very important in solving the numericals, because now you are able to put the value and get the result. That is not a big thing. You know how to solve, how to multiply, how to divide, that you know. What you don't know, that is the concept. Hence, you will know that concept, then easily you can, after putting the value, you can get the result by just giving importance of the unit. Unit is very, very important, because unit, how will you get correct unit? Then you will get correct unit only by putting the values with unit. Then after cancelling up and down, suppose you have written some value, then unit will cancelled out. What will remain? That will be the final unit. Then now I am giving some concept of numericals, giving just examples I will give, and then you can understand. Here just I am giving first example I am giving you. Calculate the energy of 1 mole of photons of radiation whose frequency is 5 into 10 to the power 14 hertz. See how easy the numerical is there. Calculate the energy of 1 mole of photon. What is the energy of 1 mole of photon? That you have to calculate, and they have given the frequency. Then you know that E is equal to h nu. H value you know. Planck constant value you know. Nu is the frequency. Then frequency value is given. Hence easily you can calculate the E. H is equal to Planck constant value you know, 6.626 into 10 to the power minus 34 joule second. Unit is important, joule second. And nu is given 5 into 10 to the power minus 14, 5 into 10 to the power 14 second per second. It is given. Then you just put these two value with unit, then you will get the energy E, 3.313 into 10 to the power minus 10 joule. See, this is the energy of one atom. This is the energy of what you calculated E by after putting the value of H and nu, that is for one atom. But you have to calculate for 1 mole. Then now you know mole concept already I have taught. I have given so many numericals on sheet. Then now very easy for this energy what we calculated for one atom. Then for Avogadro number, just you multiply by Avogadro number, means 6.022 into 10 to the power 23. Then these atom will convert. For one atom, what if you got the value? Now for this Avogadro number, how much? That is equal to 1 mole. Avogadro number is equal to 1 mole. Then now after multiplying, you will get the final result. That is 199.51 kilojoule per mole. In joule also you can write, in kilojoule also. Kilojoule if you want to write, then you have to just in joule you are knowing, divide by 1000, then kilojoule. Otherwise joule also you keep it, no problem. Then see how easy is the you can say numericals. Here I want to tell you photon for 1 mole. Actually, photon, only by telling photon, all photon will not have the same energy. This you keep in mind. Just like in mobile currency you are keeping 10 rupees also, 1000 rupees also, 500 rupees also. Then by the word currency, they are not thinking that always same money. It may differ, 100 rupees also, 500 rupees also, 200 also, 1000 also. Like that way, here photon depends upon the value of new frequency. What of frequency is there? What type of frequency is there? What frequency is there? Accordingly, photon will have energy. Every photon may differ in energy depending upon a new. This you keep in mind. Very important things I told you. Don't think that 1 mole of hydrogen or 1 mole of chlorine or 1 mole of hydrogen will have same energy. No, because nu will differ. Frequency will differ, that's why energy will differ. Energy of photon will differ. Hence, you should know what is the frequency. Okay. Now, second question I am going to discuss. This is also all are easy. Only that you have to think over. Don't become nervous by seeing the question. Question may be long, but you should understand. Okay. Then you will solve the numericals. Now question I am telling. A 100 watt bulb emits monochromatic light of wavelength 400 nanometer. Simple question is there. In every house nowadays bulb is there. Then from the bulb light is coming. Then suppose bulb is of 100 watt. Then a 100 watt bulb emits monochromatic light of wavelength they have given 400 nanometer. Calculate the number of photons emitted per second by the bulb. Very simple question. You have to calculate the number of photons. How many photons it is emitting per second by the bulb. Then see here, only relation you should know. That is very, very important. After that, formula you use and you will get the result. Sometimes one formula, sometimes two formula. As the many formula you are using, that is considered as easy, tough and tougher. Then now here you can see the power of the bulb. Power of the bulb is 100 watt. Then 100 watt means 100 joule per second. This is important. 1 watt means 1 joule per second. Then 100 watt means 100 joule per second. Then now you should calculate energy of 1 photon. You calculate the energy of 1 photon. Then energy E is equal to, now you know, H into nu. E is equal to H nu. Always keep in mind formula. These are the common formula. E is equal to H nu. Then now again you know that nu is equal to C upon lambda. Already last class I discussed the these numericals based on frequency. Then C was C lambda into nu. I have discussed, I told you. Then now here E is equal to H nu and nu is equal to C upon lambda. Then after that put all the value, H value, C value, lambda value, all value you put. Then you will get the value of energy. The H value you know, Planck constant 6.6226 into 10 to the power minus 34 joule second. And light, C is light, 3 into 10 to the power 8 meter per second divided by lambda. And the lambda value is given. that is in nanometer, convert it into the meter. Means 400 nanometer means 400 into 10 to the power minus 9 meter. That relation you know. 1 nanometer means 10 to the power minus 9 meter. Then 400 means 400 into 10 to the power minus 9 meter. After solving, you will get 4.969 into 10 to the power minus 19 joule. This is the energy. Automatically all unit will be cancelled. Only joule will remain. Then the joule you will write. This also in a common energy is represented in joule only. Then now this you got energy you got. Then how will you get energy you have calculated? Then how will you calculate number of photons emitted? Then number of photons emitted, that is equal to total you can say here in the beginning you have 100 watts means 100 joule per second. Then how much number of photons? Then 100 joule per second divided by energy of one photon. Energy of one photon. Then total energy divided by one photon. Energy from one photon. Then you will get the number. Very common, by a common sense. Total energy you are knowing from the bulb, 100 joule per second, and here you will calculated energy from one photon. Energy from one photon. Then just divide it from the one photon, then you will get the total number. Then total number will become, means after dividing 100 joule per second divided by this energy of one photon. Then you will get the final result 2.012 into 10 to the power 20 per second. See how easy the question. Only you have to use your mind. The formula you should know, that is important. Now one more this numericals I want to discuss. Then I will stop here. Then see, question is there, the threshold frequency nu 0. Threshold frequency is known as nu 0. The threshold frequency nu 0 for a metal is 7.0 into 10 to the power 14 per second. Calculate the kinetic energy of an electron emitted when radiation of frequency hits the metal. See, nu is given, frequency value is given which hit the metal, that value is given, nu is equal to 1.0 into 10 to the power 15 per second. And that also threshold frequency is also given, that is 7 into 10 to the power 14 per second. Two frequencies are given. Threshold frequency, that is the minimum frequency required to remove the electron from the metal, that is given, and you have to calculate the kinetic energy of an electron emitted when radiation of frequency nu is equal to hits the metal. Then see how it is there. Formula already I have discussed, that h nu minus h nu 0, that is equal to kinetic energy, means half mv square. This is the formula. Then say in this formula means h nu minus h nu 0 is equal to half mv square. That is the kinetic energy you have to calculate. Then h is common in both, h nu minus h nu 0. Then here h value you know, nu value is given. Again h value is given and nu 0 value is given. And then what is that? You put the value, you will get the kinetic energy. Then h value you know, Planck constant value, nu value is given. Then just by putting the value 6.626 into 10 to the power minus 34 joule per second. That is the H value. A new value is given. That is a 1.0 into 10 to the power 15 second per second. 15 per second. After that, that value is also given. Then you put both value, means threshold frequency value is given, and then you solve it. Means again I am telling you, H nu minus H nu 0, that is equal to kinetic energy. You have to find out kinetic energy. Then first H value you have put H and nu value, which is coming on the metal, minus this threshold frequency, H into threshold frequency. That value you have kept 7.0 into 10 to the power 14 per second. Then after putting this value and solving, you will get the final result 1.988 into 10 to the power minus 19 joule. See how easy is the question. H value is common. H value is common, hence you can keep H outside also. Then only inside the bracket it will be nu minus nu 0. That is called to kinetic energy. Then put all the three values and you can get the result. That will be joule. Then now I am stopping only here today, and again next class, next lecture we will meet. Thank you.